You are welcome to Latvian State Institute of Wood Chemistry. Institute is a state research organization founded in 1946. There are working in this moment 116 employees, and our turnover in previous year was 4.9 million euros. We have defined our mission, vision, and main research avenues. Our mission is the development of knowledge-based, environment-friendly, low-waste technologies for obtaining competitive materials and products from wood and other plant biomass for sustainable utilization of natural resources for economic, social, and ecological benefits. Our vision is a modern research center of wood and other biomass with broad research infrastructure potentialities and tradition-based creative and dynamic research staff open to new ideas and science challenges. The main avenues of research is fundamental studies in the field of wood science, wood and polymer chemistry, applied studies for obtaining innovative products and materials from renewable raw material resources, wood and plant biomass. We have defined three main excellences of our institute staff. Our main experiences there are the first, wood and wood materials with upgraded properties for construction. It is protection of wood, modification, renovation and maintenance, including historical buildings and our heritage. The second excellence is biorefinery approach for producing chemical compounds and products and obtaining of biofuel from wood, its waste, recyclable materials and other type of biomass. And the third excellence is production of green chemistry products and green polymers from wood and plant biomass and its processing residues. Once more, you are welcome to our institute. Now we present you our infrastructure, our equipments, our machinery and our experiences in this biorefinery field.
Wood is not only a raw material, but also a material in its own right. At the Institute, we develop wood and wood-based products and characterize and evaluate them in simulated and also in real-life conditions. The objective is to extend the use of wood and wood materials in construction and living environment in a sustainable way. For innovative material production and evaluation, we have both laboratory and also pilot-scale devices and specially developed conditioning rooms. A multifunctional modification device is used for different wood treatment processes at pilot scale. The device is capable of performing thermal modification, vacuum pressure impregnation, hot oil treatment and also others. For initial processes and material optimization, we use also laboratory-scale wood impregnation autoclave. You use hydraulic press with the built-in thermostat and process automation for obtaining pressed wood-based composite materials, such as plywood, glued wood panels, sandwich-type products, particle board, chipboards and fireboards. As the developed materials are designed for engineering applications, the mechanical properties need to be tested and evaluated. Bending, compression, tensile, shear, torsion and inner bond strength can be tested on 3 static material testing machines with different force cells for precise measurements. Impact properties are analyzed on the versatile pendulum impact tester. Non-destructive analysis of elastic properties is done by the impulse excitation technique. Surface energy, wetting angle and adhesion strength, as well as changes in these properties for different materials, are evaluated with contact angle meter and tensiometer. At the microstructural level, light microscopes are used for identification of wood species, material structure characterization, investigation of fungi and visualization of biodegradation processes. At submicron scale, the scanning electron microscope enables structure characterization at high resolution. To evaluate material performance in real-life conditions and to predict the service life of the products, laboratory agar block tests for root fungi are performed. For weathering evaluation, we use accelerated weathering testers, which can reproduce the damage caused by sunlight, rain and dew in shorter period of time than naturally. The climate chamber is used to simulate natural humidity and temperature fluctuations in order to test the material performance close to real exploitation conditions. We also perform natural weathering and biodurability tests in real-life conditions for optimized material systems and prototypes. The Institute is also home to the world's leading life cycle assessment software, CIMAPro, that contains the latest science-based methods and databases for assessing the sustainability performance data of the developed products, materials and technologies.
The 50-year-long history of research in the field of polyurethane chemistry contributes to the Institute's extensive and renowned experience in bio-based polyol synthesis, development and testing of resulting polymeric materials. Polyurethane materials are developed from different sustainable feedstocks, such as rapeseed oil, cellulose production side stream, tall oil and lignin, and also recycled PET. The Institute has the necessary equipment to characterize the chemical composition and physical properties of developed polyols. The developed technologies and synthesis methods have been validated not only at laboratory scale, but also using pilot-scale production equipment, such as 50-liter batch chemical reactor and 20-liter vacuum evaporation equipment. Polyurethane foam production is carried out at laboratory scale, testing PU foaming kinetics using foamed equipment, where technological parameters such as foaming start, gel, string, and rise time are determined. The developed PU materials are also upscaled using industry-relevant equipment, such as spray foaming machines, providing in-house production of material for further tests, and analysis using a fully equipped machine shop. The developed PU materials are subjected to vigorous testing to characterize their general properties. Rigid PU foams are applied as thermal insulation material. Thus, the thermal conductivity coefficient is measured. Thermal properties of polyurethanes, as well as other polymeric products and adhesives, are tested using DSC, DMA, TMA, and TGA equipment. Flammability characteristics and fire safety class needs to be determined if material is applied in the construction industry. So we carry out small-scale reaction-to-flame tests and material analysis using cone colorimeter. Furthermore, formaldehyde emissions from materials are evaluated by the formaldehyde discharge test installation. We analyze thermal degradation using high-resolution TGA equipment, with which a modulated TGA experiment can be performed, in addition to typical TGA analysis. Moreover, the evolved gas from TGA can be analyzed using chemical analysis equipment such as GCMS and gas phase infrared spectrometer. We have also extended our research direction in the field of microorganism biomass obtainment by generating know-how in biological process, kinetics, and applying modern model-based and control tools to obtain enhancements in both design and productivities of complex biomass cultivation processes. Solid and liquid fractions of microorganisms cultures are separated, analyzed, and processed for various research needs, including growth medium composition, optimization, product biosynthesis, enhancement, downstream process development, etc. Fully automated bioreactor systems for running microorganism cultivations are available both in laboratory and pilot scale, resulting in an investigation and development of technology readiness level from 2 to 5, including obtaining and biorefining microalgae biomass, cultivating bacteria and filamentous fungi cultures for plant growth, stimulation and protection against pests. For efficient processing, the microorganism biomass can be easily separated from the growth medium and or concentrated by using the dynamic cross-flow filtration system. Furthermore, a mixer with 30-liter drum volume is used for modifications of lignin as a plant fertilizer, while the plant growth evaluation is done by Rhizoscan and Oxytop instruments. Modern software development platforms such as MATLAB, Python, COMSOL Multiphysics, Autodesk, and Design Expert are used in routine research and engineering work for process, mass and energy balances, dynamics, economics, and design calculations. The application of modern modeling tools and software enables in-depth process understanding, which is essential in assessing the scale up and technology transfer potential for each biotechnological process and product.
Biorefinery research areas are related to the processing and separation of biomass and its components: cellulose, hemicellulose, lignin, and extractives. Cellulose as a main component of the wood has an established research direction on its own, based on developing and testing cellulose fiber materials: paper, cardboard, fiberboards, molded fiber products, microcrystalline cellulose, and nanocellulose. Since the scientific direction was created decades ago, when pulp and paper industry was active in Latvia, researchers have accumulated knowledge, skills, and experience for both fundamental and applied science in cellulose chemistry and technology. At the Institute, the pulping process and pulp production from wood or other plants is done in a laboratory-scale, custom-made automated pulping reactor. Fibers are only separated and developed in mills, but also characterized and evaluated to suit the final application. Paper or cardboard handsheets are made in a laboratory-scale paper machine, and an automatic coater is used to improve the properties of paper with natural or synthetic substances. Full spectrum of paper testing procedures include evaluating mechanical properties of paper with tensile, burst, and tearing testers, as well as surface properties, air permeability, and optical properties. We produce nanocellulose suited for different application in a microfluidizer. After cellulose, lignin is the next most abundant natural polymer with a high potential for obtaining valuable products, either from wood, bark, or other plant biomass. Separation of the biomass chemical constituents is done by hydrothermal or mechanical activation and disintegration with up to 20 kg per hour capacity to prepare the raw material for further processing, such as sequential extraction of biologically active components with a reduced extraction time. For evaluation of the raw materials or obtained products, oxypress is used to determine the resistance to oxidation of oils and fats. Modification of wood byproducts and lignins is carried out by various methods, including chemical and mechanochemical conversions. Wood plastic composites are universal in engineering materials based on both virgin and recycled polypropylene, as well as on their blends with other polymers, including polylactic acid, which are filled with functional wood byproducts. The composites can be obtained with modern processing equipment such as two twin-screw extruder and injection molding machine, as well as by rolling and pressing with the following injection molding composite blends. Microwave technologies are particularly developed at the Institute, resulting in two original pilot-scale construction for microwave or pulsed microwave assisted pretreatment of plant biomass for lignocellulosic cell wall degradation, with a focus on effective water extraction of the main constituents and secondary metabolites from plant biomass. Additionally, a pilot-scale batch reactor has been set up for extraction to obtain betaline and perform chemical synthesis in laboratory pilot tests. Solid fuels or high-quality pellets are produced in limited quantities for research purposes and tested in a pelleting press for small-scale production. Fuel pellets' energy density is upgraded by microwave treatment in an original construction microwave torrefaction reactor, combined with modification of pellet structure with waste bio-oil. Pellets are obtained, modified, and tested for mechanical and physical properties by breaking tests, attrition, elemental analysis, heat of combustion, and etc. As to the hemicellulosic part of biomass, a bench-scale reactor system modulates the industrial furfural obtaining process and is additionally used for catalytic and non-catalytic pretreatment of several biomasses. To reduce recalcitrance of lignocellulosic biomass for further production of value-added products, we have several pretreatment reactors. The periodical steam explosion reactor is used for diverse biomass pretreatment to rupture the tissue of the main biomass components, converting the raw material into fibrous particles. The 7.5-liter hydrothermal treatment autoclave is a simple and attractive physical wet biomass pretreatment method without hazardous chemicals or solvent, mostly producing oligosaccharides. In biorefineries, high temperature technologies are often the final processes for valorization of the obtained byproducts arising from pretreated or raw biomass. For such purposes, we have several pilot-scale equipment units. The continuous flow thermoreactor produces anhydrous sugar-rich bio-oil from biomass with 1 kg per hour capacity in a superheated steam system, while the bench-scale screw reactor is used for catalytic production of levaglucosenone. The external heating rotating tubular retort is suitable for thermal processing of biomass with operating temperature from 100 to 900 degrees. Next to bio-oil, char is obtained, modified and characterized to produce carbon materials with controlled properties. So, on the laboratory pilot scale, corresponding to TRL 3 to 4, we have developed several pretreatment, extraction and processing reactors for obtaining fuels, bioenergy and value-added products. The processing of biomass is dominated by physical and chemical activation, fast and slow pyrolysis, torrefaction, hydrothermal treatment, densification and extraction.
A sound analytical approach to wood chemistry is important for understanding and controlling biomass conversion processes into chemicals. In some cases, classical analytical methods are the most straightforward approach to analyze the chemical composition of soluble samples, as well as specific characteristics, such as moisture content or the kappa number of pulp. In case of natural substances, wet chemistry is a must in sample preparation by hydrolysis, distillation, or different extraction techniques. At the same time, we pay special attention to modern cutting-edge methods that provide detailed knowledge about wood-based products and the reaction mechanisms that lead to these products from laboratory scale up to pilot scale. The 6 laboratories of the Institute are equipped with the most appropriate analytical instruments for each cause. Analysis of volatile compounds is first of all done by gas chromatography with mass spectrometry or flame ionization detection. Analytical pyrolysis coupled with GCMS enables characterization of liquid and solid products for identification using the NIS database. Even the most traditional methods such as spectrophotometry can be applied in various ways, starting with portable devices for color and gloss investigations in the field to highly automated robot-friendly spectrophotometers. Liquid chromatography is a pervasive analytical discipline, and the Liquid Chromatography Center is a comparatively new unit in the Institute's structure. For qualitative and quantitative analysis of the products of biomass hydrolysis, pyrolysis and extraction, we use ultra-high performance liquid chromatographs with different detectors, RI, UV, ELS and MS, among which the high-resolution tandem mass spectrometers should be pointed out, giving an unprecedented chance to identify unknown compounds at even the lowest concentrations in complicated matrices. At the same time, it must be admitted that analysis of natural substances is a great challenge, even with the best of equipment. So the Liquid Chromatography Center is a perfect place for students to carry out their master's or doctor's thesis research. Apart from analytical works, there is equipment for the preparative separation and purification of biomass-based chemicals as valuable products to prepare for the transfer from bench scale to pilot scale. The analytical and testing equipment is a support system throughout the general biorefinery concept, combining all the research directions of the Institute.
Our recent activity is the construction of pilot-scale hangar in our yard of Institute. This will be hangar with different type of pilot-scale equipments with idea to increase the technology readiness level from 1 to 3, which level is developed in our laboratories, up to the level 4 to 6, which is pilot scale level, and it is very important for cooperation with industry for implementation of our research and development in real business life. This hangar will be ready in the next year, and you are welcome to visit our institute in this time, and thank you for your attention, and I will be happy to see you in the nearest future in Latvian State Institute of Wood Chemistry.